Good afternoon, everybody. Good morning, wherever you are. My name is Christina, and it is my pleasure to welcome you to the official unveiling of the MatSight software by PlasmaSolve. Before we begin, let me share some organizational points with you. If at any point throughout the presentation you have a question, feel free to write it into the chat of the Microsoft Teams. And then at the very end of the presentation, we'll have a Q&A portion where we will address all of those questions. If, however, you would like to ask a question directly, we welcome you to do so as well. But please, again, wait for the very end of the presentation, for the Q&A portion, and use that little raise your hand button to signify that you would like a question to be asked. I'd like to ask you to keep your microphones muted throughout the stream so that we don't get any interruptions. And then, if you would like to ask a question, I will ask you to turn the mic on. Our speaker today will be Adam, our CEO and head of consulting. And he will start by presenting our company before getting into the introduction of the software itself, and he'll present all the available applications. He will cover also the technical specifics of the software and how it is actually run on the computer. Furthermore, he will inform you about the pricing, and he'll also show you how you can utilize MatSight for your projects. So, welcome everyone again, and please, let's give the stage to Adam.
Good morning, good afternoon. I looked at the status of the registration for this event not a long time ago, and I was happy for two reasons. I was happy to see that we were just a few people short of 100 people registered for the event. And I was happy to see that about a third of these people were people we already had the chance and the privilege to work with. And so today, before I go into details about PlasmaSolve and MatSight and all this stuff, I want to pause and I want to say thank you. I want to say thank you all for working with us, for trusting us, and for supporting us in those 8 years that PlasmaSolve has been in the market. It is also thanks to you that PlasmaSolve has evolved from 3 enthusiasts coming right out of the university into an established vendor in the segment of plasma devices, and more specifically plasma coating devices, that is offering simulation consultancy, big data analytics consultancy, and general process troubleshooting and process transfer consultancy. I think we already knew quite a bit about plasma already when we began, but over those 8 years, I dare say that we assembled a team of over 10 subject matter experts who understand not only simulation and plasma, but also the related technologies and all of their strengths and weaknesses, be it PVD, be it PECVD, ion etching, ion sources for ion milling, satellite electric propulsion, or most recently, gas conversion and plasma catalysis. And I feel humbled by the fact that we as a company have been trusted by some of the most influential stakeholders in our industry. I feel humbled by that, and I feel the weight of responsibility on my shoulders for making sure that the intimate details of these people's and these companies' equipment and processes that flows through our company every day remains confidential and remains safe. I'm also sensitive, however, to the question that many of our leads and prospects are asking, and frankly, many of our customers are asking as well. And that is the fact that they actually often appreciate the usefulness of simulation, and they like the predictive capability of what our models and what our software solutions can deliver. But they also ask the question whether it is possible to have these solutions in-house for further prototyping, because we are sensitive to the fact that sometimes you simply cannot send equipment or process details to a contractor, be it for convenience reasons, contractual reasons, or legal reasons. And so today, I called this meeting together, and I'm so happy that so many of you were able to join, because from this day onward, the answer to this question from our end is a clear and decisive yes. We have been running simulations internally. We have been doing modeling internally for the past 8 years. And in those 8 years, we have been continuously improving our software. We made various iterations on it. And over those 8 years, we were never happy enough with it to make a standalone product out of it. But this year is the year where we say, okay, the PlasmaSolve software is mature enough, the PlasmaSolve software is documented enough, and the PlasmaSolve software is stable enough so that it can be released as a standalone product to the whole world, to all the plasma engineers and plasma coding engineers out there. The name of the software is MatSight. That is the brand name we adopted. And we like to think of that as the next evolutionary leap in Industry 4.0, and more specifically in plasma process simulation and plasma equipment simulation. MatSight is not a monolithic software. It consists of individual simulation modules or apps, each distinct for a specific purpose. The April 2024 lineup, or the series of apps that we are releasing today, is coincidentally a set of 4 simulation applications. All of them perform physics simulation. We have the target erosion app, aimed at engineers developing sputter cathodes and companies developing sputter targets. We have the large area app, which is specifically tailored to the needs of operators and developers of inline coaters and roll-to-roll coaters. We have the 3D uniformity app that allows you to simulate coatings on real 3-dimensional substrates, most probably for tribological or decorative applications. And we have the global model app, which is sort of a multi-parameter, multi-domain simulation tool. This is what we are releasing today, and this is what is becoming available today. But the list is by far not final. We picked these 4 apps because we've been doing consultancy for several years. And based on our experience with these 4 apps, either individually or in combination, we are able to address and to solve over 80% of all the consultancy projects we engage in. That is why we decided to release these 4 applications precisely. The other modules that are coming later this year or maybe at the beginning of next year may not even be simulations. So for example, we even have a big data processing module in the works that allows you to analyze your machine logs at a glance. And we will be, of course, releasing them to you as we go. So I will get into more detail about these applications in a minute. But before I do, let me just dedicate 2 slides to the philosophy of the software. I boldly claimed that we see MatSight as the next evolutionary leap in plasma process and plasma equipment simulation. So I think I should specify that a little further, because there have been legacy solutions for plasma simulation and plasma coding simulation. And I just want to mention how or where we differentiate as opposed to where we are consistent. I think the main point where we are consistent with all the simulation and modeling know-how of the past decade or 2 is the physics. We are not reporting here or publishing here any revolutionary approach to treating physics. We are very much aware of the amazing work that the giants of our industry did on the topic of coding process modeling and coding process simulation. And we try to stand on the shoulders of those giants and look at the different physical mechanisms and chemical mechanisms that they studied, identify those mechanisms which are the most important for a given challenge, for a given application, and distillate the best out of this work and make sure that it gets into the MatSight software. But there's also a few differentiation points. Historically, many codes for plasma modeling, many softwares for plasma modeling were designed in such a way that the numerical algorithm was driving the user interface and the user experience. In MatSight, you do not have to worry about the numerical settings. By making MatSight a set of focused applications, the numerical settings can actually be adjusted automatically, and the default settings that MatSight is giving you will probably work for about 98% of use cases for which you use the software. In those remaining 2%, you are welcome to use the consultancy hours and support hours that come with the software. And of course, the PlasmaSolve team is going to be very happy to assist you on that. Similarly, in the legacy simulation softwares, you needed quite a lot of physics expertise and very often also fundamental data like cross-sections, reaction probabilities to run the simulations. This is also something we want to get away with MatSight. And that's why we structured the software into the modular architecture I foreshadowed before, whereby we have one dedicated app for one specific challenge. And that app, so we're not selling a general simulation solver with which you can simulate everything and anything. We're selling a toolkit of tailored solutions that cover the most common problems that a plasma equipment engineer, a plasma coding engineer, or a process engineer is facing regularly. And finally, we also try to differentiate ourselves on the software level. It is understandable that the legacy codes and legacy softwares were not always great in terms of documentation and maintenance, because they often derived from decades of work of different PhD students and postdocs at universities. We had the advantage of starting from scratch. And we tried to use that advantage to the fullest. So all the physics solvers that we're using were implemented from scratch, but using OpenFOAM, which is potentially the most well-known open source simulation framework. All of the MatSight is written in Python, and all of that is equipped with tests, with automated integration pipelines. It has a thought-out and modern software architecture, and it has a documented API. So to make it clear, we're not quickly packaging something that we have in-house and trying to make a product of it. We're trying to establish an ecosystem that will not be here for 3 years or 5 years or 10 years, that will be here for 15 years and hopefully even beyond that. So this is kind of the same message in a picture. What you typically got when you got a plasma simulation software was the following 2 layers, right? You got a particle and cell algorithm, a DSMC algorithm, a GPM algorithm, and based on those, you implemented different physics models. We have these as well. Like I said, we did not come up with some magic AI simulating physics or anything. It is still physics simulation, what we are showing here. And we have those, we implemented those in OpenFOAM, and they are actually open source. So if you're an academic researcher, we will gladly give these to you free of charge. But the MatSight layer that we are introducing today is another extension of these solvers, which saves a lot of work to the operators of the simulation software, because historically, if you wanted to simulate, for example, coding uniformity on 3D parts, well, you had to get a charged particle solver, you had to get a solver for neutral particles, you had to get a Poisson equation solver, and then you had to glue them together and somehow run them to get the simulation result. And along the way, you probably had to, supply some cross-sections, reaction data, and so forth. In the MatSight universe, the predicament is different. you have a 3D uniformity app that already knows that you are going to be simulating 3D uniformity, and it automatically calls the solvers that it needs to perform the simulation. So you, as a user of the 3D uniformity app, specify literally the CAD file of the part that you want to code, the type of process, DC sputtering, ArcPVD, HiPIMS, PECVD, ion etching. You specify the process power, gas pressure, gas composition, and the throw distance. You click run, the application does the rest and returns to you the spatially resolved coding thickness, coding composition, and energy bombardment on the part that you are coding. So by adding the MatSight layer, we are making the entire simulation process much more user-friendly to coding engineers. And to make that even user-friendlier, each app comes equipped with predefined templates. So even if you buy the 3D Uniformity app, which already is quite user-friendly, I would say, you still get some template configuration files from us. One of them, for example, for 2-axis rotation in DC sputtering, one for 3-axis rotation in ArcPVD, and so forth. And you can build on these templates to implement your challenges and implement your processes in the software. So this is what MatSight is. It is an additional layer which makes the simulation procedure much more user-friendly and much faster. So let's have a look at the individual apps. I want to lead in with the target erosion app because for many of us doing PVD processes primarily, the target is where everything begins. The target erosion app is an application which allows cathode component developers and target manufacturers to ensure that the target material is utilized to the maximum potential. And with this app, you can optimize primarily two quantities. The first is target utilization, that is how big percentage of the target material is used for the deposition as opposed to how much is wasted, and also target lifetime, which is mostly driven by over-erosion and by cross-corner effect. And if you can suppress over-erosion and cross-corner effect, as we will see in an example in a little bit, you can actually prolong the lifetime of the target significantly. In our practical experience from consultancy projects, I think we were able to achieve, by tuning the magnetic field, for example, up to 20% waste reduction in targets by slightly adjusting the magnets. With respect to the lifetime, we were able to get a boost of as much as plus 40%. We're also trying to think about the ROI of these applications for our customers. And we think that, of course, depending on what target materials you are using and how many targets you are running through every day, we think that if the app allows you to utilize 20% more of the target material, then the investment into purchasing the software and running it to optimize your targets and your cathodes could return after as few as 30, 40 targets that you sell or that you burn through, depending on what your company's specialization is. The application is based on a Monte Carlo algorithm tracing electrons and ions in the proximity of the cathodes and anodes. It is tailored to high-power setups in the kilowatt range, and we've applied it successfully all the way from 3-inch magnetrons to 4-meter ones. It supports circular, rectangular, and rotary cathodes, and even if your target has some non-trivial profile or patterned profile, you can actually load it into the simulation because it supports direct import of CAD components either from STL or from step files. The typical output that you get from the target erosion application, the primary output that you get, is of course the number, the target utilization, but what goes hand in hand with it is the spatially resolved erosion rate. Here we see a time snapshot of the erosion rate in a dual sputtering system, in an MF dual sputtering system. So as you're probably guessing, the cathode on the right is the cathode, whereas the other electrode is in this snapshot, the anode. And we can look at it from various angles, and you see that there are clear over-erosion patterns in the corners of the racetrack. You can also sweep through the simulation, visualizing the plasma density and identifying potential hotspots and electron hotspots on the anode or on the opposing cathode, which I dare say is pretty interesting. But what is even more interesting and even more practical is doing parametric studies with it, right? Because, describing the current system, that's great, but the question driving us is always, how do I improve it? You can test with the erosion app the sensitivity of the erosion to the gas pressure, power, target composition or gas composition, or the magnetic field. On purpose, I will show you the pressure first. I will sweep through 0.3, 0.45, and 0.6 pascals, and when I initially do that, you'll probably see nothing. If I zoom in on that, and if you look really close, you will see that there is a very subtle difference in how the erosion rate in this over-erosion spot changed. Visually, this might not seem as much, but if you had MatSight here and if you clicked into the over-erosion spot, you would actually see that there is a tiny change of 4% in the over-erosion groove, which may seem insignificant, but actually the 4% change in the depth of the over-erosion pattern translates to a 4% reduction of the lifetime of the rotary target. So this may actually not be as much, as little change as it seems. But ultimately, understanding over-erosion is not the goal either. We want to get rid of it. So let's try to sweep the magnetic field. Let's try to change the magnetic field. And I'm going to change it from 80 millitesla on the surface in the one extreme case, all the way to 20 millitesla in the other extreme case. And you see that if I go from 80 to 60, the over-erosion got significantly better. If I further go to 40, you see the erosion becoming much more even, and ultimately at 20, I'm seeing a very nice symmetrical racetrack. There is still an over-erosion on this side, but it is almost perfectly compensated by the over-erosion in the other wing of the racetrack. So in this case, you can assume quite a uniform, quite an optimized erosion of the rotary target. But of course, you might say, well, you cannot, this would suggest that if you go to zero magnetic field, then you have a perfect erosion. This is, of course, not true. So let's see how that begins and how that behaves in more detail. Oh, and before we do, I should also mention that just by doing this simple trick of reducing the magnetic field, we were able to suppress the over-erosion and increase the target lifetime by approximately 15%. But of course, in each sputter cathode, there is such a thing as too weak magnetic field. And we will look into that on the simple example of a 6-inch planar cathode. On the left, we see the erosion profile. In the middle, we see the plasma density as these two little blobs. And on the right, we see the key observables from the model. The lighter curve is the target utilization, which is going up as we are moving the magnets away from the target. But this is not all, right? Without the magnetic field, you theoretically have the racetrack covering the whole target surface, but your plasma is not going to be very stable. So you also need to look at the plasma conductivity, and your sweet spot for operation is the point where you already have a high target utilization, but your conductivity did not start to decrease yet with respect to the baseline. So let's see what happens if I simply try to move away the magnetic assembly from the target surface. You see that the plasma is clearly getting larger and the racetrack is getting broader all the way to this sweet spot. But if I go beyond the sweet spot, you see that the nominal surface area of the racetrack may be increasing, but the plasma is literally flying away because the magnetic field is way too weak. So if I cycle through that again, you can very easily visualize how the plasma and erosion response to the strength of the magnetic field and make the decision what is the ideal distance of the target surface and the magnetic assembly. In this specific case, we went from 20% target utilization to 35%. So by finding the right magnet position, the target utilization in this specific scenario nearly doubled. And before we move on to the next step, I want to comment on the computation times. The large 1 meter or half a meter industrial setup takes 12 hours to compute on a 36-core machine. If you want to extrapolate to 4-meter cathodes, you can essentially apply a linear extrapolation. So in this case, the whole geometry was about 1 meter long. So for a 4-meter cathode, you could expect something like 48 to 60 hours. This is certainly faster than building the cathode prototype. It's probably even faster than doing experiments with existing cathode prototypes and comparing them. On the smaller setup with a 6-inch planar target, you can get the result in as little as 1.5 hours. So this is a very fast computation time, I would say. Okay, so this was about the target erosion app, but of course eroding the target and designing a proper cathode is important, but ultimately the product we are after is the coating. And we want to understand how the coating affects what grows on the substrate. For those of you who are doing that in inline coaters, roll-to-roll coaters, generally in large area applications, we have devised the MatSight Large Area app. And the MatSight Large Area app does effectively simulate how a given racetrack, how a given cathode imprint propagates onto the substrate and how it affects the film thickness, the film composition, and indirectly the film properties. You can use it to design fixtures that improve your coating thickness distribution. You can also use it in drum coaters or batch coaters to reduce the top, middle, bottom thickness variation. And it also generally allows you to maintain a constant deposition rate over the target lifetime by tuning the cathode distance, cathode tilt, cathode angle, power, or current during the lifetime of your process. For example, if your target gets 1 centimeter thinner during the process, you can use the app to find the new current set point, which will lead to the same deposition rate. Now, if you're running inline coaters, I will be so bold and say that the ROI here is nearly instant. Whenever you need to make a change, whenever you need to make a modification, you know best how much it costs to have a downtime of 1 day or 2 days on an inline coater just to test a hypothesis. So if you are doing any development, any upscaling, any retrofitting on an inline coater, I dare say that using simulation in that process has a nearly instant return on investment. The large area deposition application again works on the basis of kinetic treatment of sputtered particles traveling between the cathode and the substrate, and it supports DC, MF, and high-pump sputtering alike. It supports flat and curved substrates, which are moving, and just like the target erosion app, it allows you to import the geometries directly from CAD files so that you don't have to draw any elaborate geometries yourself, and you simply ask your construction department to send over the step files, which they just simplify a little bit. To give you an example, we will look at the very same coater that we simulated in the previous example of the target erosion app. So we have 2 rotaries which are coating a curved foil, which is moving in the direction to the right. And we're also looking at the thickness profile along the width of the coil. And you will see that for the default case, the cathodes produce a certain thickness imprint on the foil which is moving to the right. And if we define that our practical, useful coding zone is the region where the coding deviation is not more than plus minus 1%, then we actually get a coding zone of 16 centimeters only in the base case. Now, in the attempt to fix that, it seems tempting to insert a fixture near the cathodes to suppress the coding thickness in the middle and obtain a coding zone with a larger width, right? If we do that without further consideration, it can easily happen, as you can see with this hemicircular fixture, that you go too far and that your useful coding zone is actually decreased. You see that there is a clear effect on the substrate thickness, which now has a dip in the middle, but you can also see that this fixture is going way too far and reducing the thickness in the middle by a too large factor. So the next logical step is moving the fixture a bit further away from the cathodes, and this actually turns out to be the sweet spot for us here, because with this specific fixture position that has to be within plus minus 2 centimeters, let's say, the coding thickness or the width of the coding zone has increased from the original 16 centimeters to about 24 centimeters, which is a significant increase. Now imagine testing this experimentally, right? If you wanted to compare different fixture geometries, how many days it would take, how many weeks it would take to do that. If you have the simulation app that will guide you through the process, it will be much less painful, much less demanding to incorporate, for example, a cathode with a new metal, because this deposition imprint is going to be metal-specific and gas-specific. So I think the time savings on this specifically are tremendous. You can also get a similar effect by moving the cathodes closer to the substrate. You see that in this case, the width of the coding zone is even larger. It is 30 centimeters, and if we were a bit more permissive about the thickness variation, it would probably be even more. But of course, whether it is a good idea to move the cathodes closer to the target or not, that depends on the coding that you're trying to grow. And to understand whether this is going to impact your coding properties or your coding quality, you can always combine the large area deposition app with the target erosion app or with the global plasma model and see whether the ion bombardment and other plasma properties which are affecting the coding are changing in any significant way. The computation times on this app are, I would say, better than fast enough. So for this large area coder, it took 1 hour to perform this simulation. So if you went to a 4-meter coder, again, a linear scaling would apply, and you would get your result in about 4 hours. But what if your substrate is not planar? What if it is more elaborate, like a drill bit, a milling tool, or whatever else you might be coding? For those of you, we devised the MatSight 3D Uniformity app, which allows you to visualize variations of thickness, variations of coding atomic composition, and to an extent a variation of coding properties on realistic three-dimensional parts. If you're running batch coders, if you're a coding center or a job coder, this can save you dozens to hundreds of trial processes per year. Our calculation and our customers' calculation is that if the app saves you 20 to 25 trial and error processes, it will have already paid for itself. The application is a hybrid algorithm based on tracing neutral particles and charged particles. And thanks to that, it is supporting DC sputtering, MF sputtering, high PIMs, ARC PVD alike, and you can even use it for PECVD and ion etching. I think we may be the only vendor of simulation software and services that can actually simulate the growth of coding and the distribution of coding thickness in processes which are ion-driven. We're certainly not the only ones for the neutral-driven DC sputtering. But if you go to HyPIMS and ArcPVD, we may actually be the only ones who can simulate these processes, which are primarily based on ions. Naturally, we're talking about 3D components, complicated geometries, so the direct CAD import is also a feature of the 3D Uniformity app. And what is best, it supports out-of-the-box part translation and part rotation. So let's see what it looks like. One type of study that you can do with the 3D Uniformity app is comparing different processes, comparing different process set points, and understanding how they impact the distribution of your coding on the part that you are working with. Here we see a very fashionable example of the bipolar plate for hydrogen fuel cells. And in this example, we coated it with a typical DC sputter PVD process at typical average conditions, a typical arc PVD process, and a typical HyPIMS PVD process. I think the element in all of those was just simple titanium, just for the demonstration. But already in the simple case, you see that the sputtering PVD is much more ballistic, much more view factor based, whereas arc PVD is based on ions, and the particles that are leading to the coating deposition are following the electric field curves rather than the straight trajectories, and HyPIMS is somewhere in between. So if we take a closer look, you will see that the bipolar plate coated by sputtering PVD is actually suffering from highly undercoated walls of the channels, which are coated in a much better way in arc PVD, and HyPIMS is, well, something between DC sputtering and arc PVD, as you would expect. And of course, here we are comparing three extreme cases, DC sputtering, arc PVD, and HyPIMS. You could also use the app to visualize what would happen if you change the bias voltage in either of these processes, if you change the gas pressure, if you change the power of your cathode, and how that impacts the coating distribution on your component. You could also see how different elements are deposited, because lighter elements are going to have an easier way of penetrating these narrow trenches and narrow channels. So I think this is nice, but many of you are coding 3D assemblies and loading them kind of like this, like these bevel gears, right? And if I showed you a static simulation, just like I was showing in the previous case with the bipolar plate, well, then for a realistically loaded coater, this is probably what you would get. You see a coating coming from one side where the cathodes are, and the other part is uncoated. So the question is, does MatSight support the rotation of these parts? And I'm saying that because, of course, it can. The flexibility of the software allows you to revolve the part in the simulation and integrate so that you obtain a full 360 deposition in these bevel gears undergoing two-axis rotation. And that opens up possibilities to a range of interesting studies. In this one, in all cases, it is arc PVD. We varied the distance between the bevel gears, and you can clearly see that there is such a thing as an ideal distance between your components. If the bevel gears are too close to each other, you get over-deposition on the outer tooth of the gear and under-deposition on the inner side. Same for the second lowest distance. This distance, which was, I think, about 35 millimeters, you already get quite a nice and even deposition on the teeth, which gets even better if you increase the distance further. And then, depending on your thickness goal, you can use MatSight, you can use the 3D Uniformity app to design the optimum loading of your coater and of your components that you are coding. But I looked at the list of people who registered, and there were at least 20 people doing tribological and decorative codings. In those coders, you're running 3-axis rotation, usually. And I bet you are wondering whether MatSight can do that as well. Well, I'm happy to say that it can. In 3-axis rotation, as we see on these milling tools, you can visualize the same things that we've seen in the previous examples. You can quantify the deposition rate to assess the film thickness. You can quantify the energy flux to assess qualitatively the film adhesion and film density. And if you are coding from multiple elements, which most of you are going to be doing, you can also visualize how different elements get deposited on different parts of your 3D tool that you are coding. So this is indeed a very flexible tool, and with acceptable computational costs, it really allows you to simulate fully loaded substrate holders and carousels and find optimum distance between parts, find optimum distance between parts and fixtures, and really avoid a huge volume of that trial and error that you often need to do when you need to transfer your process to a new part geometry or to a new part size. The computation times on the Uniformity app are, I dare say, acceptable. It is in the order of hours on a 36-core machine. For the fully loaded rotating carousel box, it is about 10 hours, including all the rotations. Now, I have to admit one thing. We don't run those simulations that take 10 hours. I mean, we do sometimes, but it is not always the most logical thing to do. For example, if you want to optimize just the top fixture position, you don't need all the detail in your simulation to find the right position of the top plate, right? So if we get the task of finding the right plate position for a specific process point and for a specific part geometry, we very often defeature the geometry, we smooth out the grooves and the cutting edges of the milling tools, and we run these simplified simulations where we just find the optimum fixture position. And when we have found the optimum fixture position, then we probably run one super detailed simulation with a 3-axis rotation just to confirm that we did everything right. But in these simplified layouts, even 3-axis rotation can be completed in as little as 1 hour of simulation time. And the last app that I want to talk about is the MatSight global model. In terms of visuals and visualizations, this is a bit of a difficult one because this one does not have any fancy 3-dimensional output. The global model is a simulation tool for multi-domain dynamic systems where plasma is the key component. It is a 0D model, but it allows you to perform fast and high-level investigations that takes into account the plasma process as such, as well as its peripheries, the cooling system, the heating system, the power supply with its internal characteristics, you name it. And what we typically use it for is for predicting, for example, metal ionization degree in PVD processes and ion implantation rate in PVD processes. We also use it for transferring proof-of-concept processes from small-scale laboratory coaters to large-scale industrial coaters. We also use it for PECVD quite a lot, whereby we can use the global model to assess the energy efficiency of a PVD process and precursor utilization. Like I suggested, the global model is based not on 3D simulations, but on ordinary differential equations. So the geometrical factors and the size of your device can be either obtained from other MatSight applications or you simply estimate it based on your experience. But the beauty of it is that this does not simulate the plasma alone. It simulates the plasma and its interaction with other peripheries. So you can add an ODE for the cooling system, for the power supply, and see how that interacts with your coding process. Because it is ODE based, it is not a 3D model but a 0D model, computing one DOE point takes anywhere between 10 and 60 seconds. It is extremely fast. So within one day, you can explore vast areas of your parametric space. To give you at least one specific example, what we use it for quite a lot is an example of a PECVD process. The main knobs that you can control in a PECVD process are typically the mass flow rate of the precursor and the power going to the system. And as you can see in this chart, in one of the PECVD processes that we worked on, varying the precursor flow rate versus power is changing in a very dramatic way what fraction of the power that you supply to the system is actually wasted into heating the components, heating the chamber walls. And you see that there are regions which are favorable with respect to precursor utilization and energy utilization, and then there are regions which are very unfavorable with respect to energy utilization, where as much as 60% of the total energy going into your PECVD system is actually sort of wasted or used for heating in the end. The global model allows you to perform precisely these types of high-level analyses. It also allows you to quantify the energy cost of your process. For many processes, the energy cost chart looks something like this. There is a certain minimum following a diagonal between the flow rate and the power, and the moment you deviate from this minimum, your energy cost starts to explode and can be 3 times, 4 times, 5 times higher than it would have to be in the optimum working point. So this is what the GPM is for high-level multi-domain analysis of plasma processes. Okay, so these are the 4 apps that we are releasing today. Now I want to dig into the technical specifics a little bit. I think if I got your attention at least a little bit, you're probably wondering about the user interface. And the choice we made for the user interface, which I will, by the way, demonstrate on the 3D target erosion app, is Python. Python is the heart of MatSight, and it is also what is driving the user interface. A configuration file for a MatSight simulation is a Python script where you define your components, where you define your process in a Python syntax. If this seems scary, I fully appreciate that, but I will try to explain how that is actually easier and better for everyone. Because what I haven't said is that, yes, it is Python, but it does not mean that it is a command line text-based application. We're not in the 90s anymore. Yes, the configuration file is a Python script, but you can run the Python script either in the fully automated mode, where you just see logs and textual output, or you can run it in the interactive mode, where the application interface pops up and starts talking to you in the points where you need it the most. So let's see how that works on the example of the target erosion app. If you are a user of the target erosion app, you indeed have to use the Python syntax to define your simulation. That may sound as a disadvantage, but it may also be an advantage because you can leverage for loops, you can leverage automations, you can use the simulation to generate an automatic report in a PDF or a Microsoft Word. So you get really a lot of flexibility of what you can do with the MatSight simulations and how you can integrate them into pipelines. But on the side of the Python script, you have to define your process by its pressure, temperature, gas type. You define your target through its geometry file, voltage, and power. And you define all the other terminals, again, through their cat file and their potential. Then you merge all these components together in a simulation object. And as you can see, yes, this is Python syntax, but this is essentially, if you are not proficient in Python, you can consider this a textual configuration file, right? And then you have 2 options. You run either simulation.run or you run simulation run interactive. And you either get the automated batch mode, where you get no visual information throughout the simulation run. This is ideal for automated parametric studies, for automated optimization studies, or you run the interactive mode, which I will demonstrate right now. In the interactive mode, you simply run the Python script, you simply run the Python script in which your simulation configuration is contained. So this is potentially the only point where you have to open your terminal and you type Python and the name of the simulation script. When I do that, the simulation configuration is loaded from the configuration script, and I receive in a web browser window, which is of course running on your computer, a visualization interface that allows you to check that all the components from your CAD files have been loaded correctly, they are in the right place, they have the right dimensions, and that the boundary conditions have been assigned accordingly. We're looking at the example of the target erosion app, right? So we see two cathodes there with an anode in the middle, but it is very important to make sure that your magnetic field is aligning with the geometry really well, for which you have the Geometry and B Field tab. The Geometry and B Field shows you the magnetic field in your computational geometry. You have access to various slices, so you can see what it looks like in space. And most importantly, you can check the alignment of the magnetic field with your cathodes and make sure that nothing got wrong in the process and that your magnets are indeed placed in the cathode. So before you commit, before you run the 12-hour simulation, you have an interface which assures you that everything is set up correctly. If you are a more proficient user, you can also have a look at the computational mesh, which is the discrete approximation of your simulation geometry. And you can make sure that all the key features, all the key components are resolved in sufficient detail. And if you suspect that they are not, you can always go back to the drawing board and refine the mesh size. Now, if you are happy with the pre-processing, if you're happy with what the simulation setup looks like, you can simply close the pre-processing window and we will see what happens. So if you go and click the pre-processing window, you see that you get a prompt from the simulation asking you whether the mesh and geometry were okay and whether you want to continue with the simulation. You could press no, and then your pipeline terminates. You go back to your Python configuration file, you make the fixes, and you rerun everything again. But I was actually quite happy with what I saw, so I'm going to click yes, and this is the place where the simulation would run. Of course, it would run for some 12 hours, so we just have a placeholder. And if the actual simulation was running, you would be getting useful analytics and monitoring data. After the simulation completes, you get access to the primary observable of this specific simulation app, which is the target erosion. So you can find the right angle to look at it, you can quantify the over-erosion, and you can also look at the plasma distribution in this system, which is accessible to you through a series of three-dimensional slices. So here you see the typical plasma lobes in front of the cathode, and you see how the plasma is grounding itself to the opposing electrode, which is in this part of the period acting as the anode. You can move around these slides, identifying whether there are anode hotspots or other electron hotspots in your system. And you can also look at the plasma, how is that distributed in the region between your cathode and your substrate, and make deductions, make extrapolations into what the ion bombardment on your substrate is going to look like. So this is how MatSight talks to you. It is a Python-based package. The simulation configuration file is a Python script, but when you run it, you actually get all of this interactivity. So we're trying to combine the best of both worlds, right? If you want to run a series of single simulations, you probably don't mind having to configure them through a Python script. And if you want to run a parametric study or an optimization study, you are going to be so happy about the fact that this is in Python, because you can change fixture positions using for loops. You can connect it to optimization algorithms and find optimum configurations in extremely short amounts of time. And we're not entirely closed to the idea that at some point we will make a graphical user interface also for the simulation setup, but we want to hear your feedback first. If you, as the stakeholders and customers, tell us that you absolutely need the graphical interface for the simulation setup, we'll add one. That's what will happen. But in the first iteration, we have the Python interface, and we want to hear how you like it. Because we think that wherever you need the interactivity, we have the interactivity that you need. So I'm almost getting to the end here. One last property I want to mention are horizontal and vertical integrations. This is also something which is enabled to a great extent by using Python and modern technologies. In terms of horizontal integration, we've actually seen one example of that today, and that was running a target erosion simulation and using its output as an input to the large-scale deposition app and predicting the coding thickness in the large-scale app. But you can integrate horizontally even further, and you can take, for example, the output from the large-scale deposition app and feed it into, say, third-party software for optical properties calculation. We personally have very good experience with NASCAM software by the Belgian company ICS, and it is a great tool complementary to MatSight because based on the outcomes of MatSight, it can predict optical properties, roughness, and other properties of coatings grown in large area coders. You can also integrate vertically, and that is probably best shown on the example of the 3D Uniformity app. Now imagine you're a coding center and you're coding different parts for different customers. Your customer typically sends you the part and the requirement, and if you have a simulation pipeline set up, you can ask your customers not only to send you the file, but also to send you an STL file, the part, but also to send you an STL file with the part geometry. And before DHL drops the package with the part to be coded at your reception, you can already have some simulations of the part geometry, and you can already have the first idea of what is the ideal loading of the coater going to be and how to code the part in the ideal way so that your prospect or your customer is happy with the performance properties of the coding. And we would like to see MatSight being integrated not only into R&D, but we would like it to be integrated vertically into your production process as well. And so let's get to the practical business. How much does this cost? We brainstormed this, through and through, and we decided to be very transparent about this. One app costs 15,000 euros per year per license to that specific applications. It is subscription only, and it is subscription only. It includes the application setup. It includes 48 support hours a year, within which we will be helping you with both the technical specifics and physics or engineering challenges. And we're applying no user limit within your company. We are applying no computer limit within your company. So you are free to do whatever you want with the license that you purchase for a year. It is the same across all applications. And if you just want to optimize cathodes, you subscribe only to the target erosion app. If you only want to virtually code 3D parts, you buy one app. This gives us, but most importantly, this gives you the flexibility to decide what parts of the MatSight ecosystem do you need. And in simple terms, you're not paying for something that you're not using. The pricing is as modular as the software architecture of the software. You choose what you want to use, and you subscribe only to those products. So this brings me almost to the end. To summarize, we introduced 4 initial MatSight applications today, with more coming later this year and early next year. We have the target erosion app, aimed at target manufacturers and cathode component manufacturers primarily. We have the Large Area app, aimed at people working with inline coaters. We have the 3D Uniformity app, aimed at engineers working on tribo and deco coatings with substrates that have complex geometries. And we are giving you the Global Model app, which is a more high-level, multi-domain analytics tool, helping you understand how the plasma subsystem interacts with other subsystems in your coding equipment. If you like this, and I hope many of you did, you're probably wondering what next. And depending on your expectations, depending on your experience, there are two ways this could play out. As you can hopefully understand, our resources are limited. So we are ready to give out trials, but we will be giving out a limited amount of trials, especially to companies that qualify. So if you would like to try MatSight in-house, do give us a call, do write us an email describing what your expectations are. And if you're a coding center, if you are a company developing cathodes, large area coaters that can dedicate at least half an FTE to learning with MatSight over the course of the next 4 or 5 weeks until they are proficient with it, then you probably qualify for a free trial. If you would like to see how MatSight performs in your specific use case without having to dedicate a person from your team to work with it, then we recommend to engage in a qualification project. A qualification project is when we do the simulation for you using MatSight. We simulate a case or a problem that you already understand, and then you tell us how accurate MatSight actually was in simulating that problem. We can even do it as a fully blind test. You give us a part that you already coded, you give us the process conditions, we simulate what the thickness was, and then you tell us if we were right or wrong. So when you are ultimately, what we want, what I personally want is that when you are ultimately subscribing and committing to MatSight, you will already have a clear idea that this is working for you, this is working in your environment, and this is giving you the results that you are expecting. So with this, that is all I had to say today. I will be super happy if as many of you as possible get in touch, because even if you're not buying MatSight tomorrow or the day after tomorrow, we are still super excited to hear your feedback. We're still super excited to hear your thoughts. And that's what drives us forward. That's what will help us make the software even better.
Perfect. So, thank you, Adam, for this very comprehensive introduction to our software. And with this, I would like to open the Q&A portion of this event. If you have any questions, feel free to write them or raise your hand. And before any pop-up here, I have actually received a couple in my direct messages, so maybe we can open up with those. So there was one of our clients asking whether there is a certain library of materials within the apps. So for example, if they want to use a titanium target or chromium target, how easy it is to vary these materials?
That is a very good question. So yes, there is a database of materials, and there are actually 2 databases of materials. You need one for the gases. So right now we have data for argon, oxygen, nitrogen, acetylene, and methane being the most common gases used by our customers. Depending on the other gas that you might be using, and for PECVD we also have HMDSO and TMDSO. And depending on the gas you might be using, it may be easier or more difficult to implement another gas, depending on what fundamental data is available. But I think we already have the gases that will cover 95% of plasma coating processes. On materials, the material database is constantly growing. I will not even enumerate the materials that we already have in it. It is basically all metals, nitrides of most metals that are being deposited as nitrides, quite a few oxides at this point, some carbides. It is constantly growing. So depending on what material you are depositing, we probably have its fundamental data. And if not, it is an effort of 1-2 days to dig into literature and find those fundamental data for you, which we're always happy to do.
Well, that's great news then. And I have another one here in my messages. One client is interested whether the 3D uniformity app is considering the plasma sheath or whether there is some sort of approximation.
No, it is considering the plasma sheath. If you have a denser plasma, the sheath is going to get thinner. If you have a more dilute plasma, it's going to get thicker. It explicitly solves the Poisson equation and it computes the actual sheath as it looks like around the part. If you have more parts next to each other, the 3D uniformity app can detect whether their sheaths will be overlapping or not, and what implications it's going to have on the thickness uniformity. So of course, there's approximations. I mean, all of physics is an approximation, but the sheath is treated explicitly and fully numerically.
Perfect. I'm looking at the Teams call and nobody here seems to be interested in asking any questions. So I believe that's... Oh, no, we have one. So Matthew is asking, I'll just read it directly.
Yeah.
If my timeline will not let me start your free in-house trials until later in the year, will I still be able to do in-house trials, or is that just a limited time offer?
There is no limitation on the offer at this point. If your time frame is the end of the year, it's still great if you let us know today or tomorrow or next week. We can put you on our calendar and we can, we'll count with you and make sure that there is some effort available at the end of the year. So no worries. But in any case, it's good if you could, let us know in advance. We'll reserve that time for you, and then you'll get the results when you need them.
Mm-hmm. Is anybody else interested in knowing something, or are you already considering your budgets?
I can talk. I was writing, but easier if I talk.
Definitely.
Hello. Hi. It's Aurélien from Cluny. Does MatSight record the particle flux, or does it only give the final thickness? What we can call the thickness?
Yeah, so MatSight records the particle flux. If you have different particle species, you can compare, for example, the flux of lighter species like silicon and heavier species like tungsten. You can see how they compare relatively, and whether, for example, you have regions which are more rich in silicon, which are more rich in a different component. And the apps also record particle energy, which is something you can correlate with the coating properties. If you suspect that some parts of your substrate are receiving insufficient ion bombardment, then MatSight will tell you. It does not directly predict the properties of the coatings, like hardness, intrinsic stress, and so on.
Okay.
We actually have a solution for that, but that is coming at the earliest next year. But already with all the particle fluxes, you can predict the atomic composition, you can predict the thickness or the deposition rate in terms of mass, and if you know the density, then the deposition rate in terms of thickness, and you can correlate the energy flux with the mechanical and other properties of the coating.
So can you provide the history of kind of direction distribution of during the coating on each position of a sample, for example?
How the coating was growing?
Not the growth, just before, how the particle imping on the substrate during the
Okay. Yeah.
The growth,
yeah,
but
yeah,
it's not
yeah.
directly. What we can use after that in NASCAM, for example.
Yeah. In NASCAM. Yes, so specifically in NASCAM, we coupled it to NASCAM several times. And so for NASCAM coupling, we indeed in each cell record the full distribution function of the particles, and that goes as an input to NASCAM. So really in each cell, there is the full distribution function in terms of angular distribution and velocity, magnitude distribution, and that goes into NASCAM as the full input. So, of course, this data is very large. So if you're not coupling the simulation to NASCAM, then you don't need all this detailed information. But you can turn on what we call the advanced output, and then you get the distributions in each cell and feed them into NASCAM or do some further research with them.
Thank you.
Thank you for that question. It's lovely to interact with you directly.
Great.
So others, please join in if you're interested. I have another one here, but before I get into that question, I'd just like to say that as we started this Q&A portion, the MatSight website has officially launched, so that is up and running.
Yeah. And you can find, so on the MatSight website, you will find pretty much the contents of my presentation today, as well as some additional content like use cases, case studies, validation examples from MatSight. So if you want to learn more, do visit the website to remind yourself of all the information and find additional resources. We will be updating the website as we go, so I hope it will become a handy resource.
Yeah, that was also related to one question that I got here in chat, whether this demonstration would be available in digital format after we are done with this event. So, as I understand,
yes, this will also be published online. We've used the wonderful services of the Czech Press Agency. So probably the moment we sign off, there is going to be a YouTube video, and you'll get it to your mailboxes after the event.
Yes, so no need to remember everything right now. Is anybody else feeling brave and not shy and wants to talk to us directly?
Hello, I would have one question, very practical question. How or is any calibration needed during using the simulation? So if I want to connect the simulation to the real world at the end, for example, the spot rate prediction or distribution across the whole substrate over time, what measures has to be taken to connect simulation to the real world?
Yes. So depends on the process on which we are going to work. In more exotic processes, you will indeed need some calibration. For example, you have some exotic material that you're depositing, so we ask you to do 1 or 2 calibration experiments, which we then use to find the right coefficients for the simulation, and then you can extrapolate to all the other geometries in the world with that specific process. However, and that's a great question on the bat, because for most standard materials, we have enough knowledge and enough experience to do a fully ab initio simulation. So if somebody from the hard coating world comes to us and say that they are growing titanium nitride or aluminum nitride or chrome nitride, we don't ask them for any calibration data. We just do the simulation and it works. Of course, if you're doing something fancier, doping with elements which are not that common, then we might request some calibration data from MatSight for your specific MatSight application. But the important thing is that if you sort of give us any calibration data, that data is yours. The calibration data that we are using sort of freely are calibration data from papers, from literature. In the glass coatings world, yes, I think I would say the most common elements like zirconia, titanium, silicon, silver, we have data for these elements that I would be confident enough to do the simulation without experimental inputs. But of course, if there are experimental inputs that you can provide, it only improves everyone's sleep and everyone's confidence. But there is more and more materials and more processes, because the processes are relatively standard, that we can simulate without any experimental calibration or experimental inputs.
Thank you.
Thanks for the question.
Thank you. Lovely to meet more people here in the room with us.
Yeah, everybody else is calling their VPs to see if they can get a budget from MatSight.
Oh, most definitely.
Okay, well, it's great that so many of you could make it here. We'll just peek over Christina's shoulder. Okay, we got 60 people. That's really amazing.
Hang on, there is Andreas who would like to ask a question. Please go on.
Thank you for the nice presentation. Just a quick question about the trial. How's the procedure for that?
Maybe, yeah.
Yeah, about the trial project. Well, the procedure would be straightforward. We set up a call and we discuss what your use cases for MatSight would be, what app or apps you would be interested in. And then ideally, you have some problem in your drawer that you already solved empirically. You let us simulate it. You don't tell us the answer in advance. We send you the result and you tell us if we did a good job or a bad job. And depending on the extent, it can be a complementary project or it can be a funded project. So whether it's a complementary project or a funded project with some small budget of a few €1,000, that depends on the complexity of the problem and other factors. If you allow us to make a case study out of that, it will always be a complementary project, for example. So that's really up to negotiations. We are flexible in that regard.
Okay, thank you.
Thank you for the question. I've got another one in the chat.
They keep going.
That's a good question. Christoph is asking, how is MatSight better than COMSOL?
It's not. It's different. It's different. It is, so COMSOL is primarily a fluid solver. And even though they do have a particle functionality right now, the particle functionality is very generic. If you want to trace ions or electrons in COMSOL, you have to feed in all the fundamental properties. You essentially have to have a PhD in plasma simulation to be able to compute anything, anything like we've shown today meaningfully in COMSOL. On the contrary, MatSight does not have the 2D fluid model that COMSOL has, and that is very fast and very flexible. So even internally, we are using COMSOL quite a lot in consultancy, and the two softwares play together very nicely. So sometimes we calculate something with COMSOL, the outputs of that simulation go to MatSight, or we have a COMSOL model which requires some MatSight inputs. So at this point, there is very small overlap between MatSight and COMSOL or any other of these large simulation softwares, because MatSight is simply using different methods solving different problems. So it is, I would say, perfectly complementary. On the philosophical level, I think the difference is the application. COMSOL does have a plasma module, but it is a general plasma module where you really have to understand plasma science to set up your plasma simulation. MatSight is focused on specific plasma technologies and specific plasma applications, like I said, PVD, most common PECVDs with the most common precursors, and so on and so forth. So it is a slightly different architecture. So if you ask me, those are two perfectly complementary softwares with very little overlap.
Yeah, I'd agree.
So yeah, let's give everyone a few more minutes. Maybe in the meantime, I just want to mention that on the website, there is also the information where you can meet us next. Because, for me, you're like tiny people in a computer right now. But if you want to talk face-to-face, I will be at the SVC in Chicago.
Well, I will be as well.
Week, Christina as well. Then Petr and Christoph will be at the ICM CDF. And we will be also organizing MatSight webinars throughout the year, where you can get to know the applications more intimately and where we show you how you actually run them, how you actually operate them. All of this is on the website. So if you want to talk about this face-to-face, go to the website and see where we could meet next.
Yeah, that's great to know. Daniel, please, you can ask your question.
Yes, thank you. First I want to say thank you very much for a nice presentation and very good work. So really impressive.
Thank you, Daniel.
And I have a question regarding how far you are in arc simulation. So if you can simulate, for instance, the effect of the magnetic field on the composition of the coating and or the speed velocity, velocity of the arc spot movement, and for instance the creation of the droplets. So if you are able to also do that.
So we do that, but it is not the part of mainstream MatSight, let's say. We did quite a lot of consultancy projects on arc PVD, and this has often been a part of it. I will be open. There is no ab initio physics model behind that. Things like prediction of droplets, arc velocity, ionization degree, these are more heuristic models. But we even did a Horizon project on vacuum arcs where we learned all of these things and sort of found out expressions that help us correlate the arc plasma properties with the set point of the arc. In terms of MatSight, this is highly simplified. Well, simplified in the user interface way, not in the physics way. But if you want to simulate, for example, thickness distribution on a part being coded in an arc discharge, you really specify the throw distance, the effective surface area of the arc racetrack, and the power set point, current set point, material, gas pressure, and so on. And that interpolates in our database of arc plasma properties and sets the boundary condition correctly. But yeah, I think about that, I would honestly think that maybe a consultancy project is a more fitting vehicle for investigating these things. But yeah, that's up to discussion. So if you have some challenges that you want to discuss there, I would discuss them in a separate call or in a separate meeting. But yeah, but what MatSight, for example, does take into account is that different materials evaporated by arcs are ionized differently. So if you sputter titanium or aluminum, you're going to get a completely different deposition profile on the part because one of them is ionized on average 2+, the other is on average ionized 1.1+, for example. So this is included in the mainstream MatSight. Things like droplets, arc spot velocity, that is not in the main version of the software currently, but it may get there in the next releases.
Thank you, Daniel, for the question.
Yeah, thank you.
Stefan, please.
I don't have a question, Adam, but thank you for this very nice presentation. It's a pleasure to work together closely with you, and I think you're on the right way. You have all the products now that can be offered. That's just a short comment from my side.
Stefan, and I have to say that the pleasure is all mine. It's great to interact with you, great to work with you, always.
Yeah, you've already helped us in many cases. Thank you.
And you were one of the customers who, were there trusting 3 nerds coming out of university 7 years ago, and that was a brave move. Not everybody recognized the potential back then. So thank you too.
Thank you, Stefan. That's lovely to hear.
You're welcome.
Now there are a few more nerds.
Okay, so I'm not sure how we're doing on time, but I think we're already way overdue. So if there are no further questions, it has been a tremendous honor of having you all here. I'm super happy that you found the time. Those of you on the US East Coast, thank you for getting up earlier. And like I said, if you have more questions, you either have my own email at obrusnik@plasmasolve.com, or you can use the generic MatSight email. And yeah, we're here for you. If you want to discuss anything or just ask more questions, drop us a line, set up a call, and
yes, definitely. We are always eager to talk with you.
Thank you
very
all.
much.
Have a great afternoon, have a great day, and see ya.
See ya. Thank you.
Bye-bye.
Bye-bye.
Thank you. Bye-bye.
Bye.